In the next part of our chapter, we're going to discuss a very specific mechanism which occurs as part of the derivatives reaction. And this mechanism is called the nucleophilic acyl substitution. And we're going to see that, in fact, it's the equivalent of an SN2 reaction, but it occurs on a carbon that has a C double bond O, whereas SN2 reactions only occurred on sp3 hybridized carbons. So, in order for this reaction to occur, what we're going to have is a carbon group attached to a C double bond O, and the C double bond O is attached to what we would call a leaving group. And again, the leaving groups really could be any leaving group that we've already discussed in both semesters. You can find a list of the really common ones by looking on the pKa table in the base column. The weaker the base, the better it is as a leaving group. Examples that we're going to use in this chapter are chloride, which if you look on the pKa table you would see is very near the top. Carboxylate, so that would be O minus C double bond O R, be the conjugate base of carboxylic acid, and O minus R, alkoxy. Now, in this reaction, then, we start with our reactant, which has the C double bond O attached to the leaving group. Now, in terms of naming, it's a very kind of a technical thing, but we call this black piece right here an acyl group. This is something we discussed earlier when we talked about acylation. And so what we have is an acyl group attached to a leaving group. What we're going to see is that a nucleophile would potentially react with the C double bond O carbon of the acyl group because it should have a partial positive charge. So it would be attracted, it would make a bond to that carbon, we'd push a pair of electrons out onto the oxygen to make room, because we can't have 5 bonds, and we would get this. This is something that we discussed in chapter 18 in the aldehydes and ketones chapter. We called this the tetrahedral intermediate. Now, you're going to see this little symbol throughout my notes going forward. This is just sort of a little joke that I have. What we're going to see is the tetrahedral intermediate is just going to start turning up in places, even in places where we don't expect it. So it sort of reminded me of like a comic book villain. When I was a kid, I used to read comic books. In particular, if you've seen Captain America or ever read Captain America, one of Captain America's sort of canonical villains was the Red Skull. And there's so many issues of the Captain America comic book series where there'll be some whole story going on, there's some mysterious villain, what's going on, and then in the last page, they'll reveal, oh my gosh, the villain is the Red Skull, back from the dead. And so, in fact, the Red Skull has a kind of a quote, to Captain America. One time he says, I'm like a bad penny, I just always keep turning up. And so it just sort of, the tetrahedral intermediate is like that. It's like my nemesis. It just keeps turning up. And so I sort of appended this little skull picture here. And it's just something that maybe will help you remember when the tetrahedral intermediate is there. And the reason why that's important is the tetrahedral intermediate has one important property, and that is that it is unstable. It has electron pressure from the oxygen pushing down toward the carbon, and it will tend to push out a leaving group. So that what happens in this reaction is we add the nucleophile, we get this tetrahedral intermediate, and then really whichever one of these, the leaving group or the nucleophile, is a better leaving group, will get pushed out. So if the nucleophile is better, you'll push back to the reactant. If the leaving group, on the other hand, is a better leaving group, you'll push down, push out the leaving group, and then you will get a compound where the nucleophile has replaced the leaving group. So that's a substitution. So what we have here is a nucleophile doing a substitution reaction on an acyl carbon. Okay, nucleophilic acyl substitution. The abbreviation for this, sort of in symmetry with SN2, this is SN-acyl, SNAC. What we're going to see then is that there's a fundamental set of reactions that relate the carboxylic acid derivatives by an SN-AC mechanism. So if we look at the derivatives of carboxylic acids, they all have potential leaving groups in place of the OH group of the carboxylic acid. If we compare those leaving groups, then we can see that some of the leaving groups are really good leaving groups, like chloride minus, whereas others are very poor leaving groups, like Nr2 minus, NH2, HNR, whatever, with a negative charge. And the way we know that is by looking at the associated pKa on the pKa table. So we find the leaving group in the base column, we look at the pKa that's in the middle, which is the pKa of the conjugate acid, but we call it the associated pKa. And the more negative that number, the stronger this group would be as a leaving group, the weaker it would be as a base. So we can see that there's sort of a progression. If we start with an acid chloride, our leaving group is chloride minus. That's a very, very strong leaving group. When we go to an acid anhydride, our leaving group is a carboxylate, which is an associated pKa of 5. It's not as good of a leaving group. If we look at an ester, our potential leaving group is an alkoxide that has an associated pKa between 15 and 19, so that's even weaker. And then finally, when we look at an amide, we can see that the potential leaving group is an amide ion, negative ion, amide ion, and that has a associated pKa of 38 on our table. So it's a very, very weak leaving group. In fact, we actually pretty much don't expect it to act like a leaving group on its own. So therefore, we can see that we go from really strong leaving group, very unstable, down to very weak leaving group, very stable. And in fact, what we can do is we can make anything down lower on this table from something above it. So if I wanted to make an ester, I could start with an acid chloride, put in OR minus and replace the chloride because chloride's a better leaving group than OR minus. I could start with an acid anhydride, put in OR minus and replace the carboxylate because carboxylate is a better leaving group than OR minus. The other thing about this is that we can see that as you go down this table, the derivatives become much more stable. And this is really important in situations like in biochemistry. When we look, for example, at proteins, proteins are chains that are built up from amides, where you take carboxylic acid that also has an amine on it, and you hook those together to make an amide, and then you take another one of these and you hook it up to the carboxylic acid of that one, and so forth. Make chains of amides. And we call these individual bonds peptide bonds, and we call molecules that are made out of these polypeptides, or if they're very large, we call them proteins. Now, in theory, we could have also, or nature could have also, made these things using ester bonds. But we don't see that. And most likely that is because esters are much less stable. They're much more reactive. And if there is any nitrogen around, it's going to come over, it's going to knock off that part of the carbon chain, which is then going to break this long chain of peptide bonds. We're also going to see, when you study biochemistry, you're going to see that actually the peptide bond, when it's synthesized from using translation from RNA on a tRNA and on a ribosome, that in fact the tRNA itself is an ester, and then that is used to build the chain of amides. So you can make amides from esters.